Artificial intelligence appears almost magical. You ask a question, seconds later, an answer appears, an image is generated, a video comes to life. Everything feels instant, as though intelligence simply exists inside the cloud. But the cloud builds nothing. Long before an AI model answers its first prompt, an industrial system has already been working for years. Deep underground, mining equipment extracts strategic minerals. Chemical plants refine silicon until it reaches extraordinary purity. Engineers spend years designing processors containing tens of billions of transistors. Factories costing tens of billions of dollars manufacture chips with unimaginable precision. Specialized memory is assembled. Advanced packaging facilities combine components measured in nanometers. Cargo ships transport equipment across oceans. Aircraft deliver processors worth millions of dollars. Electric grids expand. Fiber networks grow. Data centers prepare thousands of empty racks waiting for their next generation of hardware. Only then does artificial intelligence become software. Every AI response is the final product of a global manufacturing system, a system stretching across continents, connecting geology, physics, chemistry, engineering, logistics, finance, energy, and computation. Most people believe AI begins with algorithms. In reality, algorithms are simply the last visible layer. The true foundation of artificial intelligence is infrastructure, and infrastructure is where the real concentration of power begins.
Every processor begins in a place that looks nothing like Silicon Valley. There are no laboratories, no glowing servers, no artificial intelligence. Only rock. Beneath mountains and deserts lie the minerals that make modern computation possible. Copper carries electricity. Nickel improves durability. Rare earth elements enable extraordinary precision. Quartz becomes ultra-pure silicon. Every stage requires specialized extraction, specialized refining, specialized transportation. The journey from raw material to semiconductor is one of the longest manufacturing processes ever developed. Years can pass before a single mineral becomes part of an advanced AI processor. This is why supply chains matter. The digital economy is not separate from the physical world. It is built upon it. Every breakthrough in artificial intelligence still depends upon mines, refineries, industrial chemistry, heavy equipment, and global logistics. Before intelligence can become digital, it must first become physical. The AI revolution does not begin inside a laboratory. It begins beneath the Earth's surface.
Turning sand into silicon is only the beginning. Modern semiconductor manufacturing pushes engineering to the limits of physics. Silicon is purified until contamination is measured in parts per billion. Crystal ingots are grown with extraordinary precision. Ultra-thin wafers are sliced, polished, inspected, prepared for manufacturing. Then begins one of the most complicated industrial processes on Earth. Hundreds of manufacturing steps, thousands of quality inspections, atomic scale precision. Light becomes the primary manufacturing tool. Lasers, mirrors, optics, chemistry, vacuum engineering, robotics. Every discipline converges inside a single fabrication facility. One microscopic defect can destroy an entire processor. One interruption can delay global production. Modern AI chips are not merely electronic components. They are condensed engineering.
Each processor represents decades of accumulated scientific progress, billions of dollars in research, and one of humanity's greatest manufacturing achievements. The world often celebrates artificial intelligence as a software revolution. But before software transforms civilization, manufacturing must first transform silicon into computation.
Designing a processor is an extraordinary achievement. Manufacturing it is something else entirely. Every advanced AI chip must pass through machines so precise that the smallest vibration can affect production. Inside semiconductor fabs, entire rooms are cleaner than hospital operating theaters. The air is filtered continuously. Temperature changes are measured with extraordinary accuracy. Even microscopic dust particles can destroy months of work. Manufacturing has become an exercise in controlling physics itself. Light is focused with astonishing precision. Optics guide energy across surfaces measured in nanometers. Robotic systems move wafers automatically from one production stage to another. Thousands of synchronized operations occur every hour. Nothing is accidental. Everything is engineered. The factory itself becomes a machine, and every machine inside that factory exists to manufacture another machine. Artificial intelligence is often described as the future, yet its future depends upon manufacturing technologies that represent the pinnacle of modern engineering. Before humanity can build intelligent software, it must first master intelligent manufacturing.
A processor can calculate at extraordinary speed, but calculation alone is not enough. Every AI model constantly moves enormous amounts of information. Parameters, training data, intermediate calculations, model weights, predictions. Everything depends upon memory. Without rapid access to information, even the fastest processor waits. This is why memory has become one of the most strategic components inside modern AI systems. High bandwidth memory dramatically increases the speed at which processors receive data. More bandwidth means higher utilization. Higher utilization means more computation. More computation produces more intelligence. The relationship appears simple, yet building these memory systems requires extraordinary engineering. Microscopic layers are stacked vertically. Connections are measured in microns. Heat management becomes increasingly complex. Packaging grows more sophisticated. Every improvement unlocks another leap in AI capability. The future of artificial intelligence is therefore not determined by processors alone. It depends equally upon the ability to feed those processors with information at extraordinary speed. Because intelligence slows down the moment memory cannot keep pace.
A completed processor is not the end of the supply chain. It is the beginning of another. Individual chips possess remarkable capability, but alone, they cannot train frontier artificial intelligence. Modern AI requires scale. Thousands of processors working together, millions of parallel calculations occurring simultaneously. Ultra-fast networking connects every GPU into one coordinated computational system. Storage delivers data continuously. Cooling systems remove enormous quantities of heat. Power infrastructure supplies uninterrupted electricity. Software orchestrates every workload. The processor becomes part of something much larger, compute infrastructure. One chip becomes hundreds. Hundreds become thousands. Thousands become entire clusters. Clusters become hyperscale data centers. And hyperscale data centers become factories of intelligence. This is where silicon transforms into economic value, not inside the processor itself, but inside the infrastructure capable of multiplying its power millions of times. The greatest breakthrough in artificial intelligence is not a single chip.
It is the architecture that allows countless chips to operate as one machine.
Once processors leave the factory, their real work has not yet begun. Thousands of GPUs arrive at hyperscale campuses. Each processor is installed inside carefully engineered server racks. Fiber optic networks connect every machine. Ultra-fast switches synchronize billions of calculations every second. Power flows continuously. Cooling systems remove extraordinary amounts of heat. Software distributes workloads across thousands of processors as though they were one enormous computer. This is no longer a data center. It is a manufacturing complex. Not manufacturing automobiles, not manufacturing electronics, manufacturing intelligence. Every AI model, every generated image, every translated document, every scientific simulation, every recommendation algorithm eventually arrives here. Electricity enters one side of the building. Computation emerges from the other. The modern economy increasingly depends upon these facilities. Banks, hospitals, universities, governments, autonomous vehicles, scientific laboratories, entertainment platforms. Every industry is beginning to consume manufactured intelligence. The world's largest AI campuses are therefore becoming something far more significant than technology infrastructure. They are becoming industrial infrastructure, the factories powering the intelligence age.
Every supply chain contains vulnerabilities. The AI compute supply chain is no exception. Remove strategic minerals. Chip production slows. Interrupt semiconductor manufacturing. Entire industries begin waiting. Delay advanced packaging. Processors remain unfinished. Restrict memory production. Compute performance declines. Limit electricity. Data centers cannot expand. Disrupt fiber infrastructure. Clusters lose synchronization. Every layer depends upon another. Every dependency creates a choke point, and every choke point creates leverage. Throughout history, economic power has rarely belonged to those controlling every stage. It has belonged to those controlling the stages that nobody can easily replace. The AI revolution follows the same pattern. The most valuable companies are not necessarily those building the most popular applications. Often, they control the infrastructure everyone else depends upon. Invisible bottlenecks become invisible monopolies. Invisible monopolies become enduring economic power. The intelligence age is therefore not only creating new technologies, it is creating entirely new strategic choke points that will shape global competition for decades to come.
Every industrial revolution redraws the map of power. The steam age rewarded coal. The oil age rewarded energy. The internet age rewarded connectivity. The intelligence age rewards computation. But computation does not exist in isolation. It depends upon an industrial ecosystem so vast that no single nation controls every layer. Some regions possess strategic minerals. Others refine silicon. Some design processors. Others manufacture them. Some build advanced memory. Others assemble complete systems. Some provide hyperscale cloud infrastructure. Others generate the electricity that keeps it all running. Power is no longer concentrated inside a single factory. It is distributed across an interconnected architecture of dependencies. This changes the nature of global competition. Countries are no longer competing only for technological leadership. They are competing for resilience. Who can secure critical materials? Who can protect manufacturing capacity? Who can expand electrical infrastructure? Who can build enough data centers? Who can educate enough engineers? Who can finance the next generation of industrial expansion? Every answer strengthens another layer of the system.
every weakness becomes another dependency. The AI compute supply chain is therefore more than an industrial process. It is becoming the geopolitical architecture of the 21st century. The organizations that understand systems will always see opportunities long before others recognize them, because the future is rarely shaped by a single invention. It is shaped by the infrastructure that allows millions of inventions to exist.
History remembers the products that changed the world. The locomotive, the automobile, the personal computer, the smartphone. Artificial intelligence may soon join that list. But history eventually discovers something even more important. Behind every revolutionary product, there was always a revolutionary system. Railroads made industrial expansion possible. Electrical grids transformed modern cities. The internet connected billions of people. Today, the AI compute supply chain is becoming the next foundational system of civilization. Every layer supports another. Mining enables materials. Materials enable silicon. Silicon enables processors. Processors enable computation. Computation enables intelligence. Intelligence enables entirely new industries. This is how civilizations evolve, not through isolated inventions, but through interconnected architectures that compound over decades. Most people will remember the AI applications they use every day. Few will remember the factories that manufactured the processors.
The electrical grids that powered the servers, the fiber networks that carried the data, or the industrial systems quietly coordinating every layer beneath them. Yet those invisible systems will determine where wealth accumulates, where innovation accelerates, and where power ultimately concentrates. Because applications may capture attention, platforms may capture markets, but infrastructure captures dependence. And dependence is the most durable economic moat ever created. The next trillion-dollar company may build extraordinary artificial intelligence. The next generation of global influence, however, will belong to those who own the infrastructure capable of manufacturing intelligence itself. Because in every era, the winners are rarely those who simply create the next product. They are the ones who build the system every future product must eventually depend upon. That is the hidden architecture of the AI economy. That is the blueprint of modern power. And that is why the future of artificial intelligence is not ultimately a story about software. It is a story about infrastructure. Nexera, Decoding Systems, Architecting Wealth.